Hello, I'm Pyro, Thermophysical Properties Product Manager at TA Instrument. I would like to welcome you and thank you for joining us in today's webinar. If you get disconnected at any time, please use the instructions you received to log back in. You can also access various content by clicking the Documents widget at the bottom right-hand corner of the screen. This includes speaker bio and additional file downloads. If you need help at any time, click the question mark widget. Please ask any questions you may have at any time during this presentation by submitting them through the Q&A window. We will answer as many of these as possible at the end of the webinar. I'm really pleased and honored to introduce our presenter, Professor Mariano Paganelli, globally renowned as one of the major experts in the field of traditional ceramics. Back in year 2000, he developed the double beam optical dilatometer using backlight image analysis, a major breakthrough in the industry. Since then, Professor Paganelli has been awarded several patents for other optical dilatometry techniques, published a large number of papers in scientific and technical magazines about ceramic materials and technology, and is a founding partner of Steelcare that just started marketing an innovative ceramic flooring concept characterized by a durable surface and a patented file laying system. Earlier on, Professor Paganelli was the R&D director of Marazzi, a name that I believe you all in the tile industry recognize, and in 1989 he was appointed professor at University of Modena in Italy. Professor Paganelli holds a PhD in chemistry from University of Modena. The title of today's webinar is Optical Contactless Measurements of Shape and Dimensional Changes at High Temperature. For the tests, Professor Paganelli and his team used TA Instrument's new Optical Dilatometry Platform, ODP 868, that has been recently launched, and it's an innovative instrument that can perform heating microscopy, both horizontal and vertical optical dilatometry, and fleximetry studies of samples ranging from traditional ceramics to advanced ceramics, casting powders, both plant ashes and metal alloys. Thank you, Mariano, because your contribution has been very valuable indeed, and I believe that the result is outstanding. Enough said, let's switch to the microphone to Mariano. Thanks a lot.
Thank you, Piero. I'm pleased to be here today to tell you about optical contactless measurement of shape and size dimension at high temperature. Why should we care about shape and size changes? After all, to measure the melting temperature, you can simply pick up a grain of material like the one shown here, put it inside the thermal analyzer and get a nice measurement of the melting temperature. Looking at the specimen at the end of the test, you will see only a shiny little drop of molten material. But real material melts in different ways. Forget all what you know about dilatometry and thermomechanical analysis. We can go far beyond these limits and analyze size and shape changes which occurs while the material is heating up to the final melting. And this is the result of the image analysis transformed into numbers. Real material may behave in a variety of different modes during the melting. Thanks to the image analysis, we can recognize characteristic shapes that the material acquired during the melting. But we can go even far beyond, reaching boiling temperature and bubbling temperature, which for some specific application is fundamental. And there is no other choice to do this. Optical image analysis is a combination of three complementary technologies. The first one is the heating microscope. We analyze the image of the sample through backlight direct beam. And we can go as far as the complete flattening, the complete liquefying of the material. Materials rarely behave as smoothly and predictably as the melting of ice. Many materials do not show a melting temperature. They show a melting behavior, meaning to say that upon heating, they change their shape from the solid material at the beginning down to the complete molten state. This series of changes in the shape is given by the development of a liquid glassy phase in the inner side of the material itself. The first detectable size change is the sintering beginning. Once the glassy phase develops inside the material, it starts pulling together all the particles, and the shape changes size but not shape. At a certain point, the liquid glassy phase emerges on the surface of the specimen, wetting the surface. At this point, the surface tension of the liquid phase exploits its strength and start modifying the shape of the material. This is the point that we identify as softening point. All the material is dense and the surface is wet. Now, the presence of a liquid on the surface starts changing the shape, driving the shape to a sphere point if the surface tension is high enough, or to a bell point, as we have seen in the previous movie. Further increase in temperature, the interfacial tension between the liquid drop and the substrate start decreasing. Then the drops start flowing on the substrate, reaching a half sphere point, and further increasing temperature, it keeps flowing on the substrate, flattening on the substrate. The last characteristic shape is the melting point, which is defined by a variety of different standards. But this is not all, because even this melting behavior is affected by heating rate. If the very same material is subjected to a ballistic heating, so instantaneous heating, the behavior in melting changes dramatically. This is the case of the cast powder, an additive for the steel industry, which is poured onto the molten steel. Can you imagine any heat treatment faster than that? So even at 80 degrees per minute, which is already a very fast heating rate for a measuring instrument, the behavior is not quite similar to what happened at 1,200 degrees per minute. There are several international norms to define the feasibility test procedure. The two mostly used are the ASTM D1857 and the ISO 540. But they refer only to the field of the fusibility of ashes. Indeed, the feasibility test has become a standard quality control procedure in other industrial fields, like glasses, glazes, pigments, and many other materials which are supposed to melt under heat treatment. The quality controls of the frit behavior during the melting has become a standard procedure for the glass industry. The example shown refers to the same glass. The center material is the glass as it is. The left material is the glass which was thermally nucleated. and the right material is the glass which was chemically nucleated. They have a completely different behavior, even though the chemical composition is exactly the same. And there is no other way to know it. This result can be better understood looking at the graphical elaboration of the images, where we can see that all three samples melt at the same time, but following three completely different paths. The image analysis can be used for the measurement of the surface tension at high temperature. This is possible using the Young-Laplace equation. Despite the beauty and the apparent easiness of the formula, this mathematical formula has no analytical solution, because developing the formula, it turns into a fourth-grade differential equation. Then the only way to solve the Young-Laplace equation, which by the way was written in 1815, is through numerical iteration. What we can do, as you can see from the formula, in the formula we have two parameters, R1 and R2, which are the two radius of curvature of a sessile drop. A sessile drop is a drop with obtuse internal angles. P1 and P2 are the pressure on the two sides of the surface of the drop, which depends on density. Now, with image analysis, we can numerically fit the profile of the drop and exact the two radius of curvature. Now, the problem remains into determining the density of the molten glass at high temperature. How do we do? Thanks to the optical dilatometer, we can measure the size increase of a glass specimen up above the glass transition temperature, when the glass enters into the liquid state. And we can follow this expansion while it is already in the liquid state for hundreds of degrees. Then we can extrapolate this part of the curve up to the temperature that we want and extrapolate the density at high temperature. Managing this way, we can use the heating microscope as a Young-Laplace tensiometer at high temperature. The other technology is the optical dilatometer. The optical dilatometer makes use of two cameras at high magnification, which are spotting the two extreme parts of the specimen, only a few hundred micron of the two parts of the specimen. This machine, this technology is a world apart, is not competing with push rod dilatometers, because push rod dilatometers cannot go above the transition temperature where the materials start behaving plastically. They are limited to the elastic state. Besides the fact that, besides this, within the elastic range are much easier and cheaper than an optical dilatometer. But if you need to go above the transition temperature, entering into the plastic state when the material starts becoming even sticky, and the minimum pressure that you put on it is going to deform the sample, you are not measuring anything real anymore. So the optical dilatometer is the only choice. In many fields of research, the scientist is not interested in the melting, indeed. He is interested in the early development of the glassy phase, which is promoting the sintering. All traditional ceramic is like that. Then, it is of utmost interest to find the temperature at which the sintering rate or strain rate reaches the maximum in order to design the fastest possible heat treatment. Here we can see how the machine works. The two black lines in the upper part of the screen are the images of the two last 100 micron of the tip of the specimen. As you can see, they are not flat, they are rough. It is close to impossible to machine a sample with a precision of 1 micrometer. The roughness that we can see here are about several tenths of micrometer. If you are pushing on one of these things, one of these hips, with the push rod, you may see the flattening of the hip, not the real expansion of the material. Now we can see here a live representation of how it works. The material is being heated. The black line is the expansion. The green line is the speed of expansion or strain rate. And we can follow the expansion of the material. The two images are moving apart because the material is becoming longer. But this is not going to last forever. Rising the temperature, we reach to the point where the glassy phase start developing and start pulling the particle together. Then a fast shrinkage start happening, and the two images start moving toward the center. This process is very fast simply because here we are applying a very quick heat treatment, 80 degrees per minute. Once reached the minimum dimension, the process inversed. The material starts swelling, the dimension starts growing. Then entering into the cooling, the two lines start closing again toward the center, reducing the size again. So it's a very complex, and there is no other machine that can show you exactly what it is happening. Beside that, as you can see, while we are rising the temperature, the two surfaces are not flattening, are becoming more and more rough. This machine is invaluable. This technology is invaluable in the study of the maximum strain rate. The maximum strain rate is the dream of ceramic scientists. And in order to get close to that magic number, they run hundreds of tests because they must approach this, but they cannot reach it, because if they reach it, the push rod dilatometer is showing fake numbers. Here we can clearly see in this graph that the sample is submitted to a heat treatment, the red line, where it goes up to 1400 degrees C, and then followed by a cooling. The red line is the size change of the material. It's keep rising, so expanding up to about 1000 degrees C, and then it starts rapidly shrinking, reaching a point of minimum dimension. Immediately after starts swelling. So what does this mean? What is the information that we can gather from this? Simply the maximum strain rate. Deriving the dimensional change against time, we find the temperature of maximum strain rate. And we know with one test that if we overcome this temperature, the material will start bloating. The nice thing is that we can do this also on tape cast thin films, because we are not applying any pressure. So even if the film is 100 micron thick, even if the film cannot withstand its own weight because it's too soft, we developed a specific sample holder to keep it in place, and we can follow the dimensional changes during the heat treatment. This is like a dream for this kind of technology. This is an example of thermal expansion measured on a glass rod. The picture on the left depicts the glass rod before the test and after the test. The curve shows a rising attitude with a constant slope up to the glass transition temperature. Beyond that, the slope sharply increases, reaches a point of maximum, and then falls down. It looks like the classic thermal expansion run with a mechanical dilatometer, because it looks like, but there is a relevant difference. In the push rod dilatometer, the curve starts going down because the push rod is pushing. So it is deforming the sample. And this happened maybe 30, 40, 50 degrees above the glass transition. Here we are hundreds of degrees above the glass transition. This is the true softening. It's the same softening that we see with the heating microscope. And the proof is the shape of the sample after the test. The two tips are rounded. The material is becoming shorter, not because there is something pushing on it, but because the liquid glassy phase is pulling. This is my favorite. This is something impossible. This is measuring thermal expansion on coarse-grained, loose quartz sand. Something inconceivable. Also because nobody has ever seen what really happened at these temperatures. I mean, quartz sand is a beautiful material because undergoes all three mechanisms of volume change. Change of the length of the chemical bonds, change of the angle of chemical bonds, and change of crystalline structure. And this graph contains all three volume changes. This is another beauty. This is a cycled heating, a slow cooling on a time base on a glass specimen, window glass specimen. In the graph on the left, the dotted line is the heat treatment. The solid line is the size of the sample. We can see that the size increase while heating, decrease while cooling, increase while heating, decrease while cooling. On a time base, it doesn't look so nice. But on temperature base, we can see something fantastic. We can see the size reduction due to the volume change of the glassy phase during the slow heating. And this happened the first time you heat up and cool down. All the other three, heating and cooling, are perfectly overlapped. I challenge any mechanical dilatometer to do the same. The field of research of plastic material is even more intriguing because we do not only see the size change involved to the glass transition, but we also see the crystallization. This material is cycled up to 130 degrees, down to 100 degrees, up to 130 degrees, down to 100 degrees. And we see the specimen becoming transparent and opaque, because of the crystallization. CT accuracy. This is the biggest question about optical dilatometer. Because at first sight, our resolution is about 2 orders of magnitude lower than mechanical dilatometer with optical encoder. 2 orders of magnitude, it looks a lot. But let's do some math. We bring the image on the image sensor with a resolution of 300 nanometer per pixel. So 0.3 micron per pixel. This is the limit of the optical system. We cannot magnify anymore. If we use a specimen 50,000 micron long or 50 millimeter long, the number of virtual pixels, remember that we split the image on 2 cameras, is 50,000 micron divided 0.3. So we are actually measuring the material with a resolution of 1 part over 166,000, plus or minus 2, because we use 2 cameras. So each camera is plus or minus 1 pixel, 2 cameras is plus or minus 2. If the CTE of the material is 5 by 10 minus 6 per Kelvin, and the temperature interval is 400 degrees, the increase in length of the specimen will be 50,000 micron by 5 by 10 minus 6 by 400, which is 100 micron. The uncertainty of the measurement is plus or minus 2 pixels, or plus or minus 0.6 micron. The uncertainty of the measurement of the CTE is 5, which is the theoretical, plus or minus 0.03, 0.03 10 minus 6 Kelvin. So we are talking about 3 by 10 minus 8. We are absolutely comparable with mechanical dilatometer, with the invaluable advantage of not touching the sample and entering into the plastic state. You may say, well, and if the sample melt inside the machine, nothing happened. The only thing you waste is a sample holder with the specimen sticked on it. The last technology is the optical fleximeter, which is used to measure the flexion, the deflection of a beam. The deflection of a beam may arise from elastic or plastic stresses. If the deflection is coming from elastic stresses, it may be of very little, it can be very little in size. We are talking about less than 100 micron. In order to get an accurate measurement of such a small variation in the flatness, we use a 3-point absolute optical fleximeter. So we make use of 3 cameras spotting in 3 points of the specimen. So this becomes virtually insensitive to the size change of the measuring system of the machine. This movie depicts a test run on an aluminum rod, which is not bending at all. Doing the math on the 3 points, we can see that the black line, which represents the drift of the measurement, is within 5 micron. So it's more than enough to say that with a 100 micron movement, we get a good accuracy. This is the deformation of a 2-layer material. We have a 2-layer material, and how do we know if the deformation that we see is elastic or plastic? Somebody consider this an impossible task, but we can solve it, because if we reheat the material, then we can see how it moves. If it stays flat and does not move, like the aluminum rod before, we may state that the 2 layers of which the material is made have exactly the same thermal expansion coefficient. But if instead it moves like this picture shows, so it becomes concave, it is moving downward, faster and faster, means that the thermal expansion coefficient of the layer 1 material, the material which is underneath, is higher than the material which is layer 2 on the surface. So underneath it is expanding faster and the material bends downward. Suddenly, the curve inverts the pattern and becomes flat. What's happening? It's happening that one of the two materials has entered into the plastic state. So the elastic stress given by the difference of thermal expansion coefficient is absorbed plastically. So this nice temperature is the coupling temperature between the two materials. When the two layers are bonded at high temperature, it becomes of critical importance to know at which temperature the two materials bond together and start behave elastically. Then, if we go further deeper in the analysis and overlap to this curve the thermal expansion of the two layers, we see something extraordinary. This is the thermal expansion of layer 1. And this is the thermal expansion of layer 2. Look what happened. At the coupling temperature, they match perfectly. And they also match perfectly at room temperature. What does this mean? It means that despite the fact they have a great elastic stress around 570 degrees, at room temperature, the material is completely free of stresses. This is the ideal situation, because materials very rarely have a linear thermal expansion. The thermal expansion is close to never linear. It goes up and down. Then the fact that the material, the two-layer bond at a high temperature makes it unpredictable to know what will be the stress at room temperature, unless you measure it. Another nice information that we can get about using the optical fleximeter is the pyroplastic deformation. What is pyroplastic deformation? It's deformation at high temperature under its own weight. There is a term which is much more known, which is creep. Creep indeed represents the deformation under load. And when the deformation is without application of load, the common term is becoming pyroplastic deformation, deformation of the specimen under its own weight. Now, let's do some math. If we take a beam with a distributed load, with thickness of the beam h, density ρ, modulus of elasticity E, distance between the supports L, it will show an elastic deformation of gamma. Now, we can still apply the same formula in case of viscous deformation. The formula is still valid if we change the modulus of elasticity with the modulus of viscosity. And if instead of measuring the absolute deformation, we measure the shear rate, the speed of deformation. The nice part of this is that viscosity becomes inversely proportional to the shear rate. If we exchange the two, it turns out that if we measure shear rate and we know all the other parameters, we can measure viscosity in a range that is out of the reach of traditional rotational viscometer. This is an example of the measurement of viscosity on a glass rod. The red line is a heat treatment, and you can see it is a stepped heat treatment that reaches a constant temperature at 560 degrees. At 560 degrees, we measure the strain rate, and using the formula above, we can calculate the viscosity, which is exactly what it is. So instead of using an extremely expensive, high temperature rotational viscometer, with this technology, you can run also this kind of experiments. But the master of all pyroplastic tests is on traditional ceramic, because nobody has ever seen what happened. And they do thousands of experiments trying to identify which is the best batch, the best formula. And eventually they find it. But here we can define it in one test. This is the heat treatment. Now we'll show you a comparison between two batch formulas which are used by two different manufacturers to manufacture the same material. Look what happened. This is the pyroplastic deformation of body 1. Make the derivative. And this is the shear rate of body 1. This body shows, say, a typical behavior. Rising temperature, the viscosity of the glassy phase drops according to the Arrhenius law, then the shear rate increases. Look at this. The blue line is the pyroplastic deformation of body 2. The difference is impressive because the total deformation is less than half. Only because of this is a better body than the other. But what is really impressive is the derivative, the shear rate, because this body goes against the Arrhenius law. Rising temperature, the shear rate or the viscosity is decreasing. How is it possible? Because this glassy phase is interacting with the matrix, and crystallizing is not going to be more and more viscous, but it is going to become less viscous. And this, on the industrial perspective, is a tremendous advantage. This is really crazy. I mean, the interference of the glaze layer on the deformation. Sometimes the glaze itself may interact with the upper layer of the body, giving rise to weird behavior. And this is an example. Before deforming downward, this material is deforming upward, becoming convex. And this is a nightmare. Any ceramic scientist knows that these things must be avoided, but they don't have the faint idea of it. They cannot measure it. So they have to wait for the product to get out from the industrial kiln. Here, it's a matter of a few minutes to run the test. The last feature that we added to this technology, since we have two thermocouples inside the furnace, is the possibility to run differential thermal analysis. And despite the odds, and despite all the trend in differential thermal analysis, which has driven the technology to the use of smaller and smaller specimens, we did the opposite. What about if I want to do it on a bulk specimen? And this is a very nice example of melting and crystallization on a glass ceramic powder. During the black line is the heat treatment, and the red line is the heat exchange. The peak upward represent crystallization, the peak downward represent melting. So look what happened. We start from the glass ceramic in the form of glass. During the heating, it is crystallizing. Further increasing the temperature is melting. Then start the cooling. We are starting the cooling with a molten material. During the cooling, it reaches crystallization temperature and it crystallizes again. Then when we start heating up again, it is already crystallized, then we see no effect. While reaching the melting temperature, we see the melting, so we have the proof that it was already crystallized. After that, in the cooling, it crystallized for the third time. These are really very nice experiments to run. Okay, now I'm closing this presentation about the measurement of behavior with a citation of a renowned economist, Peter Drucker. If you can't measure it, you can't improve it. Thank you for the kind attention.
Thank you, Mariano, for the informative presentation. Even when using the powerful new TA instrument ODP-868, I am myself impressed by the quality and variety of data you were able to get out of one single instrument. Ladies and gentlemen, before opening the Q&A session, I'd like to remind you a recorded version of this webinar will be archived and available online through the TA Instrument website. Please submit your questions through the Q&A window. We'll answer as many as possible.
Okay, so the questions are coming. So Mariano, we have the first question. It's what is the largest sample size you can place in an optical dilatometer?
Okay, so the 868 can accept sample up to 60 millimeter long in the horizontal configuration and 20 millimeter tall in the vertical configuration. So,
okay.
These are the size limit for optical dilatometry.
So pretty straightforward. And Harald is asking, what is the repeatability of the temperature measurement for accurate CTE calculation?
Well, we usually evaluate the repeatability not on temperature but on CTE, given that the measurement of CTE is accurate by the thermocouple, and the measurement of temperature is accurate by the thermocouple. The variation may be given by the measuring system on the thermal expansion. We normally are within the standard range for mechanical dilatometer, which is 0. As we have seen in the slide for the repeatability of the accuracy of the measurement, we are at 0.03 minus multiplied by 10 minus 6.
Okay. Thank you. We have here another question from Shona. Is it possible to add pressure to the sample during measurement?
Pressure, what do you mean? The measurement of thermal expansion or measurement of flexion?
I believe in any of the tests you showed during your presentation.
So we can add physically a weight on the sample. During the fleximeter test, we can put a weight on it. The weight must be a refractory material. The furnace is not equipped to apply an external load on the sample.
Okay, yes. So it's, for the time being, the answer is no pressure capability yet.
No pressure capability.
Okay, we have here another question from Osman. What is the shape that yields the best results for heating microscopy tests?
Well, in the past, we always suggested the 2 by 3 millimeter cylinder, because it proved to be the shape and the size that yielded the most reproducible shape recognition analysis. However, for many labs, this represents a hurdle because of the need to meet standard requirements, as for instance, ASTM, which asks for 19 millimeter pyramids, or ISO, which asks for 12 millimeter pyramid or cylinder 3 by 3 up to 9 by 9. No one standard regulation foresee the use of 2 by 3 millimeter. Anyway, thanks to the introduction of the 868 and most of all of the morphometrics analysis, the dependence of the results upon shape and size is significantly reduced because the shape recognition algorithms have been dramatically improved. So we get very close results from the 2 by 3 millimeter specimen up to the 19 millimeter specimen.
Okay, thank you. And here we have a good one, highly technical, to challenge you, Mariano. Does the sample need to be under vacuum to avoid beam deflection by density gradients in the air?
Well, this is really
That's
tough.
a very good one.
It's a pretty good one.
This comes from Tim. Thanks for the question.
This is we know that we have temperature gradient inside of the furnace because of the convection inside of the furnace. But for all the tests we ran and for the specific field of application that we've been developing, these gradients of temperature are not, do not affect the measurement too much. But I understand that for specific and very special material, very thin material, this may be an issue. We are not now in a position the furnace is not being designed to run under vacuum yet. This is going to be a future development.
Okay, thank you. And let me see, it's coming. Yeah, okay. So it's this is from Joseph. This is a classic one. What are the pros and cons of classic push-rod dilatometry versus optical dilatometry? Also, thanks, Joseph, because this was another good one.
Well, this is the classical doubt, when somebody wants to buy a dilatometer. Which one is the best, mechanical dilatometer or optical dilatometer? Well, for us it's not a problem because TA has the widest range of dilatometer of all, optical and mechanical. But there are some considerations that can be made. We are the first, I personally am the first to advise the use of a good mechanical dilatometer with silica measuring system if the goal is to measure the thermal expansion up to a moderate temperature, or below 1000 degrees, on a material which is always rigid. The silica dilatometer is still the best choice. But the problem is when we get into higher temperatures and when the material enters into a plastic state. Most of all, the study for the sintering process of materials. In this field of research, it is essential to avoid the hurdle of the calibration curves and to reduce to zero the interference of the pressure of the push rod. The solution is only one. Avoid a mechanical system going into the furnace in order to avoid the calibration curve and avoid to touch the sample in order to avoid the interference of the pressure on the specimen. So for each specific application, this is the analysis that should be done. What is my first use of the dilatometer? It is quality control on a metal sample or a ceramic sample up to 500, 700, 800 degrees. No doubt, use a mechanical one. But if the target of my research is to study the sintering behavior, the melting behavior, or whatever above the point, the transition point into the plastic state, the optical dilatometer is the only choice.
Okay, thank you. So basically it's up to the sample and the temperature, if I correctly understand that. It's the closer to the softening point, the more you suggest to switch to optical versus push rod.
Exactly.
This is, you mentioned metals, and Jean just asked a question about, have you run tests on steel samples? Any issues with oxidation arise from that?
Well, yes, there is the issue of oxidation, but there is also an easy way to solve it without going under vacuum. We always suggest and we use inert gas with an addition, a small addition of hydrogen. 2% of hydrogen is enough to prevent oxidation because it will eat up completely the residual oxygen that is always present if you don't purge completely the furnace. We get the specimen at the end of the test which are still shiny, even shinier than before the test. The only issue may be aluminium, because aluminium may start oxidizing very early before hydrogen can start reacting with oxygen. But for everything else, we don't see the problem. We have several instruments used in the steel industry.
Okay, and this is just, there's no official question, but I'm sure quite a few are asking the question that it's like, having hydrogen in the purging gas doesn't cause any safety problem or any compliance or need to comply with some local safety rules?
Yes, this may be an issue depending on the countries. We are talking about 1–2% of hydrogen. There are two possibilities: a hydrogen generation on site, a reactor which may work with, for example, water electrolysis, or chemical reaction, for example, aluminium with caustic soda. And this is absolutely safe because you do not have a storage of hydrogen. The other is to buy a vessel of pre-mixed nitrogen with 2% hydrogen. The percentage of hydrogen is so low that it's not even going to take fire. I mean, if you blow it on a fire, it will shut the fire down. But it is enough to prevent oxidation. In some countries, it is enough a very small amount of hydrogen into the vessel, even 1%, and the vessel is considered explosive, which is non-realistic. I mean, it is not going to take fire at all. But the solution of hydrogen generation is the hydrogen generation on site is the easiest.
Okay, thank you. So basically, it's up to the answer is up to the country, but usually up to 2%. There's no safety hazard for the lab at all. Okay, thank you, Mariano. And I believe we have time for one last question that I know comes from Magali from Brazil, and when is better to use vertical versus horizontal dilatometry?
Well, this is actually independent if you use a classical push rod or optical dilatometer, because vertical dilatometer has been designed for the purpose of reducing the pressure on the specimen. So they are ideal for sintering test. With vertical dilatometer, you can virtually reduce down to zero close to zero the pressure on the specimen. With optical dilatometer, you are sure 100% that there is no pressure on the specimen. This becomes crucial when the sample is sintering with the viscous flow of a glassy phase, and if you do the test with the horizontal optical dilatometer, the specimen may stick on the sample holder. It's not because you waste a sample holder. The problem is not the fact that at the end of the test you have wasted the sample holder. The problem is that sticking on the sample holder, it will not shrink as it would be if it would be free. So when we test material that may stick on the sample holder, it is always preferable to use the vertical dilatometer in order to get more accurate results.
Okay, thank you. I believe there are a couple of questions more, but if you don't mind, I believe that we'll be happy to take more questions on offline. Please contact your nearest TA representative. We are nearing the end of the webinar. Thank you to everybody for your attention. We really, really appreciate. And I look forward to meeting with you again shortly when we're going to have the next webinar for optical dilatometry. Thank you, everybody. Have a beautiful day.
Thank you.